Good afternoon. I'm going to just give you an overview of our experience of implementing 3D printing in a production environment. So the company I work for is SCHIVO Precision, based in Waterford. We're headquartered in Waterford. We have two sites in the UK, one in Leicester and one in Northern Ireland. So we're in about 360 people at the moment. We've certifications, as you can see there, to the aerospace standard, medical devices standard, and we're approved suppliers to Rolls-Royce, Airbus, Bombardier. We do work for companies like Waters, Stryker, and traditionally what we've done is we've been a CNC machining subcontractor. Last year we made the decision to start entering into the additive manufacturing or 3D printing world on a subcontract basis. So what we did was we partnered with a company called Stratasys. Stratasys invented fused deposition modelling, which is the process on the machines we've got on the ground in Waterford. We've two Fortis 400 machines and a Fortis 900 machine. Now the target is to have 20 machines on the ground in 2 years. And as we get busier, Stratasys are partnering with us to put these machines into the factory on what they're calling a printing bureau basis. We also have a partnership with Ramesh's group down in WIT, where there's an EOS M280 metal sintering machine, and those parts there are typical of what that machine will build. So that's in Ramesh's lab. We access it a day a week. We're dipping our toes in the water a little bit with the metal. We've learned that the metal is not quite as advanced as the plastic. So they're the examples of the two machines we've got. They're production grade machines. The one on the left is a polymer Fortis 900 machine. It can print up to a metre cubed, and the machine on the right is the DMLS machine down in WIT. So I suppose our experience, if I were to compare traditional subtractive manufacturing, that's a CNC machine, it's a CNC lathe. Many of you don't know what that is. So what that does, it takes a blanket material, it turns it, that results in a different shape blank, and then we do some 5-axis machining, and that results in that part. So there's multiple operations, there's setup costs, it's quite a convoluted process to get to that product. With the fused deposition modelling systems that we've got, the material is fed up from the base of the machine, and it's basically layered over and over and over again. The advantage of that is you have no setup costs like you have in CNC machining. It's getting cheaper, it's still on a part-by-part basis more expensive than CNC machining, but it's a lot faster, and you can get very, very complex geometries in 3D printing. In terms of the direct metal laser sintering process, it's slightly different. I hope I'm not stealing some of your thunder now, Ramesh, explaining this, but it basically sinters powder, uses a laser to sinter powder layer by layer. And again, talking about the complex geometries, you can get the killer app here is by taking the material out of that part, it makes it much lighter. That's an aircraft part. So while there's some discussion going on about the energy usage of 3D printing, in particular direct metal laser sintering, and how expensive the process is, the counter argument is that when you produce a part like this over the lifetime of an aircraft, you get that long-term saving. In terms of our 3D printing, the process is extremely simple. Take a model, that's a model of a part we've built or we've CNC machined in the past. You just send it to the printer, that's the 3D printed version of it. So rather than having setups, tooling costs, all that type of thing, you go from virtual model to a physical component in the build time. There's no preparatory kind of work that needs to be done. So from our experience, if we were to compare subtractive versus additive, so subtractive is the world we always lived in, where you take a piece of material, a work piece of material, you take away material to make a component, to the additive process which builds it up. The advantage of subtractive, it's proven technology, it's extremely accurate. CNC machines, the 3D printing companies will tell you that the 3D printers are as good as CNC machines. They're not. In terms of accuracy, they're not there. Excuse me, as yet. Subtractive manufacturing is also very cost effective when you're making multiple parts. The advantages of additive, the killer app for additive at the moment is still rapid prototyping. You can also make very, very complex geometries, and I think that's one of the things that we learned when we first put in the machines. All the CNC machinists were saying to me, these things are going to take our jobs. They're not, because 3D printers make a different type of product, or can make a different type of product. And that's the challenge, I think, for young engineers coming through, that they're unconstrained by the previous design constraints, where you couldn't get a tool in to make something. Now, you know, all bets are off in terms of what you can actually print and the geometries that you can do. The other thing is the technology can be very, very rapidly learned, for polymer at least. Disadvantages of subtractive are the setup times, the programming required for each component, and there is a high level of skill involved in running a CNC machine. The disadvantages of additive: it is less accurate. The surface finish on an additively manufactured part is not as good, and there's still a question mark around the mechanical characteristics. There's a lot of kind of sexy talk going on at the moment that Airbus are going to put components into planes, and you know, there is concerns around the mechanical characteristics of the part. That's why, you know, the partnership we've got with Ramesh's group is important, because we can do the material characterization of the components, and I think that's increasingly going to be a part of the 3D printing world for the next couple of years while we understand it deeper. You also need all the metrology capability, so it's not as simple in normal manufacturing to just put in a 3D printer and say that you're off. You do need post-processing capabilities. You're going to need some CNC capability to achieve the accuracy. If you want to mimic CNC accuracy on an additive part, and there's also post-processing. So, you know, we do heat treatment, we do coating, there's testing. You need all those capabilities to support, certainly to support metal additive at this point in its life, and not by accident. This is the latest machine from Morosiki. Morosiki were a traditional CNC machine builder, and they've identified the need for what they're calling a hybrid machine. So to the right there is a 3D printer, and it then transfers it to the left where it's CNC machining. So, you know, that's the kind of thinking that the traditional CNC machine people have realised that this thing is coming down the tracks, but they're trying to get ahead of the game on it. There's a lot of talk in the type. The area that we're involved in, enterprise 3D printing, this is from 2013, 2014, and we're gone along the hype cycle to a point where, you know, enterprise 3D printing is almost the norm. One of the things that we looked at as well is converting existing parts that we CNC machined to additive manufacturing parts. So this is a component we machined for a mass spectrometer. So what we did was we looked at, just to see where additive could change the design of a part. We looked at the key features. Then we took all the conventional machine constraints out, optimized it for 3D printing, and that's the part that we actually ended up with. So the part on the top left and the part on the bottom right are essentially the same thing. But again, we need to remove the support, which involves the CNC machine. We need to machine seats for injection nozzles and features. Other features have to be machined as well. But if you know, and I say this all the time down in Waterford, trying to listen to me. The geometries that you can get on additive parts are going to be what's going to make this technology move to the next step. It's not a replacement for traditional manufacturing. For example, you know, molds for injection molding. We can print geometries that you just couldn't machine. You couldn't manufacture by any method before. There's a lot of stuff people are saying about the thinking outside the box, and like they're printing houses in China, they're printing food. They have printed a body part. They've implanted a body part in North Carolina, and MIT have a self-assembly lab where they're looking at self-assembled components. For one of the kind of killer apps for that is that they can develop a self-assembled scaffold for seeding cells in the body. So, in terms of coming from an industry perspective, how can we capitalise on it? We use the 3D printers we've got mostly for design verification, fixturing, stuff that we're only ever going to make one of, or very low batches. And again, new concepts and geometries they just can't be manufactured using traditional methods. So I think the next generation of engineers are going to be kind of, you know, they're going to be, as I said, unconstrained by the traditional challenges of making stuff. And that's mass customization. You know, there's definitely a medical application there. But I think from a product design perspective, it's not the case that 3D printers are just going to, you know, become a new technology to make the same old stuff. Any questions? Okay. Yeah.
What industries are you getting business for your 3D printing?
We've done some medical prototyping, we've done some aerospace, and we've also done consumer electronics. So the medical My understanding is that the FDA have told all the big medical companies that if there's new technology available that can be, adopted that will, adopted that will improve the patient experience, there's an onus on those companies to adopt that technology. So medical people are very, very interested.
Are the materials that you're using approved for medical oil?
A lot of them are. There's a chart. I'll give you an example. There's one of the plastic materials that's UL approved. The UL don't have an approval on it after it goes through the printing process. Even though it doesn't go through a phase change, they're still saying there's a fundamental change, and that's why the characterization is so important. So like we do biocompatibility studies on components for medical as we get further down the line. But really, with the aerospace people, it's the characterization of substructures and all that kind of thing that's going to sell in. Like I had a guy from one of the aero companies ask me one day, how can I guarantee that every single line in a 3D printed part is fused together? And obviously you can't. So I asked him, how do you guarantee that an extruded part is okay? And his answer was 40 years, 50 years of validation. Anybody else? Great, thank you.